Hey guys, so let's go ahead and do some related rate problems and go over a systematic way of tackling these problems. So let's get started. So here we have the related rate problems are actually used for finding an unknown rate. We're looking for an unknown rate of change using a known or an unknown rate of change, right? So we're actually going to use a known rate or given information to us, known rate or just given information to us, to find an unknown rate. And that is the whole idea of a related rate problem, right? I'm going to give you guys a nice little story. We're going to talk about some rates, some numbers here and there, and we're going to use all that information in order to find this unknown rate of change that we're actually looking for, right? And then let's talk about how we're actually going to go ahead and to compute this related rate, right? So like I said, we're going to be using implicit differentiation, but we're going to be deriving in terms of time, right? And what that means is that whenever I derive an x or a y, it's all going to be in terms of time. For example, if I derive an x, I am going to have dx dt. If I derive a y, I'm going to have dy dt. If I derive an angle, for example, theta, I'm going to have d theta dt, right? That would all make more sense when we jump to example 1. But for right now, let's just leave it at that. And then before we do our problem, we need to identify, as we're reading the word problem, we need to identify the proper blank needed in the problem, right? So very important is going to be to identify the proper equation. And what I mean by equation is that depending on the problem, we're going to use different equations to solve it, right? So if we're talking about some tank being filled, then we got to talk about the volume of a cylinder, right? If we're talking about a sphere, then we got to care about what equations talk about that sphere, whether we're talking about the volume or we're talking about the surface area, or whether we're just talking about the radius. Doesn't matter. We need to see what equation, what parent equation we're using to solve this problem, all right? And then after we identify our equation, we need to identify the blank used in the equation. And that's going to be the variables, right? So depending on the equation, we're going to have different variables, and then we got to think about what variable is actually changing in our problem, right? So which rates are actually changing in our problem? Because just because we have a bunch of variables doesn't mean that every variable is changing, and that's very important. So on top of that, let's be careful with something that can actually help us in being like an answer check, right? So we need to be careful with blank, and in that blank we're going to put be careful with units, right? So units are actually going to be very, very important, and rarely we actually care about units when we in calculus, but when it comes to related rate problems, we're actually going to care about units a lot, right? And they're actually going to tell us if there's something wrong with our answer or not if we don't get the right units. So let's go ahead and do example 1 so you guys can see how we can put all these bullets together into actually tackling a problem. So here we have that the radius of a sphere is increasing at a rate of 3 meters per second, right? So here's that known rate that we have, right? We have a rate which is 3 meters per second, which is, you know, change over time. In this case, our time variable is in seconds. So you guys see how this is the known rate. And now let's talk about the unknown rate that we're trying to find. So let's keep reading the problem. So here we have how fast is the volume increasing when the diameter is 10. So there I'm asking you how fast is the volume increasing. So there, that's what I'm asking you. I want to know the rate of the volume. The rate of the volume, right? So let's translate all this stuff into math. And we're going to start off here. I already gave you guys a diagram of a sphere. And we're going to start off by writing down our given information in the given area with the picture. So here we have that the radius of the sphere is increasing at a rate of 3 meters per second. So since we're talking about the radius changing, that is going to turn into dr dt, because it tells you the change in the radius over the change in time, and that is going to be 3 meters per second, right? We already wrote that down. We're good with that. Now let's go ahead and keep reading, and it says how fast is the volume increasing. So now we got to talk about the change in the volume, right? The rate of the volume, and that is going to be volume. Our variable is going to be capital V, and it's going to be dV dt, the change in volume over time. That's what we care about. We want to see how the volume is increasing over time. But this is actually going to be a question mark because we don't know what it is. That is our goal That is our unknown rate that we're looking for, right? And they just tell us that the diameter is 10, when the diameter is 10. So we'll see how that helps us later on, right? So now that we have identified all our given information, let's go ahead and talk about the equation that we're actually going to use, right? So in this case, we're talking about how the volume is increasing when the diameter is 10, right? So it seems that we're concerned with the volume of this sphere, right? So this will require a little bit of previous knowledge, but the volume of a sphere, the equation for that is going to be 4/3, or 4/3, pi r cubed, right? So there's only two variables. There's only two variables here. We have the volume, the v, and then we have the r for the radius, right? So we got to think about this, right? So here it tells us that the radius is increasing, right? So if we have a sphere and our radius increases, right, which means that this part right here is getting bigger, is the actual volume of the sphere getting bigger, right? Are these two rates related? And we're going to say yes, right? Because if I have a radius getting bigger, the volume overall of the sphere is going to get bigger, right? And you can also see that if we change this in here, it's going to directly affect this in here, right? So once we do that, once we talked about that these variables are going to be changing our problem, because if we affect the radius, we're also going to affect the volume, then we go ahead and derive, right? So after we identify the variables and what everything means, and we have our equation, we're going to go ahead and derive. And if I derive this equation, right, when I derive v, it's going to give me dv dt, right? Because the derivative of v is just going to be 1, and then 1 times dv dt. This is how we apply the implicit differentiation, which we previously learned. So that's how we apply the implicit differentiation to the v, right? We're going to derive both sides. And here we're to derive the v. Now let's go ahead and derive the right side, which we have 4/3 pi. Well, see, this right here is all a constant, so we don't really care about it. We're just going to put 4/3 pi. Nothing's really changing there. But here, you guys see that r squared is a variable. So we're going to go ahead and derive that, and it's going to give us 3r squared. We're going to use our power rule with implicit differentiation. And since we derived a variable, we're going to go ahead and multiply by dr dt, right? Because we have our radius, and it's going to be dr dt. This radius is changing over time, so it needs its own rate of change next to it. Okay, so now we have computed implicit differentiation, right? So the idea is that we just take the derivative of every variable that is changing, not every variable, but only the variables that are changing in our problem. And eventually we're going to use all the information that they gave us, and then we're going to find our unknown rate, right? Which in this case we said that it's going to be dv dt, or also here dv dt. So we're going to go ahead and plug everything into this side of the equation to hopefully get the answer of dv dt. So let's go ahead and do that. So here we have dv dt is equal to 4/3 pi. Well, we can actually even clean this up, right? Because if we have this 3 here and this 3 here, they're actually going to cancel. So when I clean that up, I'm going to have 4 pi r squared dr dt. So now I'm going to use my given information to find my rate of change that I'm looking for. So I'm going to have 4. I'm going to have 4 times pi. Well, that's not really changing, so I don't really care. Now radius squared, something's going to go in there. And then dr dt, which is the change of the radius over time. But hey, they gave us the rate of change for the radius. They told us it was 3 meters squared, 3 meters per second, or right here also we have 3 meters per second. And we're going to put it in with its units, because remember, the units are going to make a lot of sense for our answers. So there we go. We have solved everything we have. Except that now we need the radius. We need to square the radius. But we don't have the radius, right? They never told us anything about the radius. They told us about the diameter, right? So we have the diameter. Now, can we relate the radius and the diameter somehow? Sure we can. The diameter is equal to twice the radius. Or you guys can say it as the radius is half the diameter. Whatever, it's easier for you to understand. So here we're going to put that diameter is equal to 10. So how much is the radius? We know it's half, right? So we're going to divide both sides by 2. So the radius is equal to 5. So all they gave us the diameter, we needed the radius. So we just connected those two numbers and we found what we wanted. So we're going to go ahead and put 5. But see, it's 5 meters, right? Because the radius is a length. So the radius does carry units. So let's go ahead and put that in there. We have 5 meters. So now we pretty much have everything. We just need to simplify our answer. Because we have our 4 pi, which is just a constant. That's not going to change. The radius, which we mixed it up with the diameter. We related those two. And then we have our rate of change for the radius, which was given to us, right? And we're going to find our ultimate goal of the change of the volume. We're going to see how the volume is increasing. One last thing here, right? They tell us that the radius is increasing, right? So how do you guys think this affects your rate? Is your rate just 3 meters per second? Well, it is, but there's something that's hidden here, right? And it's going to be a plus, right? Let's talk about plus, because your plus, it means your direction, right? Your volume, your radius is getting bigger, right? So if your radius gets bigger, naturally you think that your volume is going to be bigger. So since we have a positive rate of change for the volume, we expect, for the radius, we expect that since the radius is getting bigger, so is the volume, right? Because if your radius gets bigger, so does your volume. So let's go ahead and see if our answer tells us that. So this is a positive 3, right? And we know that just because of the fact that it doesn't have a negative, right? But let's go ahead and simplify. So here we have a 4 pi, which we're going to leave just there hanging out. This is going to be 25 meters squared. Let's use our units carefully. It's going to be 3. And this is going to be over per second. Cool. So now let's go ahead and multiply things. So all we got to do is just multiply the numbers, right? So it's going to be 4 times 25. That is 100, right? 4 here times 25 is 100. Times 3 is going to give us 300. I'm just going to put my pi in the back. And then I'm going to use my units here. I have m squared times m. That is going to give me m to the third over s. So there's a few things we got to talk about with our answer. Our area, our related rate answer. So here we have 300 pi meters cubed per second. So here's the idea. We have meters cubed per second, right? So we know that volume, our answers are always actually going to be cubed, right? Because we have 3 dimensions when it comes to volume, right? Usually if it's a cube, it's going to be length, width, and height. Here we have radius squared times radius cubed. So we have all these dimensions cubed, right? So the fact that we got a cubed set of units, we have a cubed set of units for our rate of change for the volume, that means that we're good to go. And also it's divided by time, which means it's a change in the volume over time. And then our answer is also positive, which means that our volume is increasing at a positive rate as you're increasing your radius in a positive rate. And that makes sense. When we make the radius bigger, so does our volume, right? So that's kind of how we put all the idea together of all the little steps here of this related rate problem. So I'll go a little faster in the next one just so I don't bore you guys, but just keep the steps consistent, right? And that's the idea. Let's come up with a recipe that we can apply to all these problems, because you guys will see that the next related rate problem is going to be, it's not going to be very similar, but it's going to be the same idea of solving the problem when it comes to steps. So here we have that in example 2, we have a 5-foot ladder who's just leaning against a vertical wall when Rosa begins to pull from the bottom of the ladder away from the wall at a rate of 0.5 feet per second. How fast is the top of the ladder sliding down when the foot of the ladder is 3 feet away from the wall? So there's a lot of stuff going on here. So I got lost in that 2 long sentences. So let's go ahead and just break it down, right? So first, we have a 5-foot ladder. Okay, cool. So here we have a little picture, right? So we always start our problems by reading our problem and then drawing a picture. Drawing a picture is going to be very, very helpful. Sometimes they'll give you a picture, sometimes they won't. As soon as they won't, so learn how to draw your own pictures. Right? So the picture here is going to be very useful so we can picture what's happening. So here we have that. We have a 5-foot ladder. So this slant here is going to be 5 feet. And then we keep reading and it says that it's leaning against the wall. Cool. This right here, this vertical thing is going to be our wall. And then it says that Rosa begins to pull from the bottom away from the wall, right? So you're actually pulling the bottom, which I'm going to say it's right here. The bottom of this ladder, you're pulling it away. You're going to pull it away from the wall. So the direction that you're going in is actually going to be to the right, because to the right is going to be pulling away from the wall. And then it's at a rate of 0.5 feet per second. So we have 0.5 feet per second, right? But what rate is that? See, here we have already pre-labeled that it's going to be the x, right? So that is the x axis. So we're changing the x coordinates at a rate of 0.5 feet per second to the right, right? So that means that we're going in what direction? We also need to identify direction when it comes to our rate. Well, it's positive, right? Our change in x is going to be positive, so dxdt is positive, which means that we're going to the right. And that's exactly what we're saying. We're pulling away from the wall, and away from the wall is to the right. So our sign tells us that we're going to the right, and so does our story. So our signs match our answer, our story. So now, let's go ahead and see what the rest of the problem has for us. So here we have that the question is, how fast is the top of the ladder, which we're going to say it's over here. This is the top of the ladder. How fast is the top of the ladder? Let's label this the bottom. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 3 feet from the wall? So they're giving us a specific scenario, right? That when the ladder is 3 feet from the wall. Okay? And they're telling us that how fast is the top of the ladder sliding down, right? Sliding down. So we're expecting this top of the ladder here to slide down. And does that make sense? Here we're relating the rate as you're pulling the bottom of the ladder with the ladder just coming down. And that makes sense because let's kind of draw something in green here. If my ladder is now here, this thing is straight, right? So it should be now down here. If my ladder is now down, if I pull this far away, then my ladder has to be over here. I know my lines are not the straightest, but you guys get the idea, right? The more to the right that I go, the lower the top of the ladder goes. And that's how it's affected. So here we're going to relate the rate between the ladder, the bottom of the ladder, so the x changing, with the y changing, right? So the rate that we're looking for is going to be our dy dt. It's going to be the rate as the y changing as we slide it down. Okay? And we'll talk about how this 3 feet from the wall scenario affects our answer, right? So the next thing, after we have drawn everything out and thought about the problem, we're going to go ahead and write the equation that corresponds with this problem. We need to identify that equation. And here, it's kind of given to you guys also, just because we're going over the example, so you guys are still learning this, that this right here is a right triangle, right? So we have a triangle, we have a ladder. Ladder problems always go with triangles. So you're most likely always going to use this equation. And the only equation that we know to talk about right triangles is going to be the Pythagorean Theorem, right? The Pythagorean Theorem. So let's go ahead and write that. And the Pythagorean Theorem is going to be x squared plus y squared equal to c. Because here we have a right triangle, and that is what we're dealing with when we talk about the ladder, the wall, and the floor. All those three things talk about a right triangle. And right after we identify our equation, we're going to go ahead and derive it. But before we derive it, we need to see what is changing and what is constant. So the x squared, is that changing? Does that deserve a dx dt? Yes, the bottom is changing, so therefore that variable is going to get its own dx dt. How about the y? Is the y changing? Okay, yeah, it's sliding down on the y. So the y is changing. How about the c? Is the ladder changing? No, the ladder is not changing because the ladder is going to be constantly the same size. Our ladder doesn't change. It's going to be steel ladder that just, boom, doesn't change. It's going to be the same length. It's going to be 5 feet all around. So when we go ahead and derive this, there's going to be 2x, right, because we use the power rule, dx dt for the fact that it's changing. Then we have 2y dy dt for the fact that it's changing. And then c squared, it's not going to be 2c dc dt because it is a constant. And what is the derivative of any constant? It is going to be 0. Okay? So now let's solve for what we want. We want to solve for dy dt. So this is our main goal, right? So let's isolate our equation and solve for that. And then we'll see what we need. So let's move over this guy, this 2x dt to the right, so we can leave the dy dt on the left. So we're going to have minus 2x dx dt. And then the last thing that I'm going to do before I have my dy dt by itself is I'm going to have the 2y alone. And that looks like a very weird t. So let's fix it so we don't get confused with any other letter. So I'm going to divide by that 2y. I'm going to have dy dt is equal to minus 2 dx dt over 2y. Then I can further simplify this. I'm going to have a negative x over a y times a dx dt, right? So now that we have solved for a dy dt, we have solved for the unknown rate that we want, we're going to go ahead and plug in everything that we know. And the first thing we should start off with, is really like obvious to us, is going to be this number right here, which is going to be our dx dt, which is 0.5 feet per second, right? Just do it over s. So that is the first thing that we know. And then we're going to talk about the x and the y. So here we got to talk about the x, and that is the x coordinate, or the x distance from the wall at this scenario that we're talking about, right? And in this scenario that we talk about is going to be 3 feet from the wall. So in this case, our x is going to be 3, right? And just to kind of clear it up, let's draw it over here because we have a lot of stuff going on over there, right? So our ladder is 5 feet. Our x distance is 3 feet. So therefore, we're going to have 3 over here for our x. How about our y, though? What is our y? They never tell us our y. All it tells us is the ladder, and they tell us our x. So how can we find our y? Well, the formula that relates these two problems, these two related rates, is going to be the Pythagorean Theorem. So we can actually find, since we have a right triangle, we can find our y having our x and our ladder, because our ladder serves as our hypotenuse. So let's go ahead and do that. So here we're going to have x, which is 3, x, which is 3 squared plus y squared equal to c squared, which is 5 squared. It's going to be 9 plus y squared equal to 25. So y squared is equal to 25 minus 9 is 16. And then we're going to take the square root of both sides. And I know that you're used to having plus or minus when you take the square root of both sides. But here we're talking about lengths, right? Our y is actually here going to be a length. So we only care about the plus 4. We don't care about the negative 4. So here we have plus 4 for our length of the y. Alright? So that means that our y in this case is 4. So let's go ahead and plug that in. So we're going to be very picky, and we're actually forgetting something. The x is not just 3, it is 3 feet. And the 4 is not just 4, it is 4 feet. So now, since we have cleared that up, we have all our units, and we have all of the numbers that we need. We have all the variables. So let's go ahead and just do a final last cleanup and check for units and check if our sign of the answer makes sense. So let's go ahead and clean up units first. So I'm going to go ahead and cancel this feet with this feet. So if you would have forgotten the feet, in this case you would have gotten lucky, But don't get used to that because it's not always going to be that easy. Sometimes the feet are really going to make a difference, or any units. And then we're going to have 3 times 0.5 over 4, right? And I'm actually going to go ahead and rewrite 0.5 as 1/2 because it just makes more sense for me. Because 0.5 is the same thing as 1/2, so I can have a nicer answer. And by nicer, I mean fractions. I know you guys don't like fractions, but in this case, it makes it easier for me. So I'm going to go ahead and multiply this. My final units are going to be feet over second, right? So let's go ahead and write that. Feet over second. And then if I multiply this 3 times 1, it's going to be 3 over 4 times 2, which is going to be 8. So it's actually not showing there. So 3 over 8. And then the last thing is going to be this negative here. So my final answer is going to be dy dt is equal to negative 3 over 8 feet per second. And that means that I have a negative rate. But what does that mean that I have a negative rate? That means that as I'm pulling away, as I'm pulling positively on the x, the y is actually getting smaller, right? Because the y is getting smaller, I have a negative rate, which shows that my y gets smaller as my x gets bigger, right? That's a negative relationship between the two rates. And that is the importance of having signs here, because we can actually talk about what the problem is doing and what is actually happening in this scenario. So let's go ahead and do some more examples on different types of related rates problems. So see you guys next time.